All right, let's dive right in. We're going to the edge of what we know about the universe, to the heart of a black hole, to tackle one of the biggest mysteries in modern physics. So, picture this. You throw something into a black hole. From the outside, things calm down pretty quickly. The event horizon just sits there, looking quiet. But physicists knew something wasn't right. On the inside, something had to keep changing, keep evolving for an unbelievably long time. So what is it? What could possibly keep growing long after the show seems to be over? Well, it turns out the leading candidate isn't something familiar like mass or charge. Nope, it's a far stranger, more slippery concept called quantum complexity.
So what on earth is that? Let's stick with a simple analogy. Imagine you've got your basic ingredients in a bowl: flour, sugar, eggs. That's your simple reference state. And your goal is a beautiful, fully baked chocolate cake. That's your complex target state. Quantum complexity isn't the cake itself. It's the absolute shortest, most efficient recipe possible. It's the minimum number of simple steps, like mixing or heating, that you need to perform to get from the ingredients to the finished cake.
Now, this is a brilliant idea, right? But for a long time, there was a huge roadblock. To actually test this, to connect it to black holes, you have to be able to measure it accurately. You need a good ruler. The problem was, physicists had a few different rulers, and they all gave different answers. Not good.
So a team of researchers decided to get to the bottom of this. They basically put the main methods for measuring complexity into a cosmic police lineup. Their mission? To figure out which one was the real deal and which ones were imposters. And here are our three main suspects. We've got the Fubini study approach, the covariance matrix method, and something called the circuit complexity method. Now, don't get hung up on the names. All you need to know is that they each try to measure the same thing, but in totally different ways. It's like one looks at geometry, one looks at statistics, and the last one literally counts the steps. Yeah, it's kind of like having three different accountants calculate the cost of a building. The first one only adds up the cost of the raw materials, the second one only tracks the man-hours, and the third just looks at the electricity bill for the construction site. They're all measuring cost, but which one is actually giving you the full picture? Which one is telling you the true complexity of the project? This is where things get really, really clever. The researchers, Ali, Bhattacharya, and their team came up with a brilliant litmus test, a simple thought experiment designed to catch the faulty methods in the act. Okay, here's the setup for their test. They looked at two scenarios. In scenario A, the Loschmidt echo, you take a quantum state, you evolve it forward in time, and then you immediately try to evolve it backward, but with a tiny change. Think of it like a round trip. In scenario B, fidelity, you do two separate one-way trips. You start with the same state, evolve it to point X, then you start over from the beginning and evolve it to a slightly different point Y.
Now, why do all this? Well, in the researchers' own words, the whole point was to test the sensitivity of the complexity to the actual path taken. In other words, does the journey matter as much as the destination?
And this is the genius of the whole experiment. If you just look at the starting and ending points, the quantum distance between them is exactly the same in both scenarios. Any dumb ruler would measure them and say, yep, these are identical.
But intuitively, we know better, right? A round trip with a detour feels a lot more complicated than a simple one-way trip. So the multi-million-dollar question is, which of our three accountants, which of our three rulers is smart enough to see the extra work that went into the journey? So the trap was set. They ran the numbers for all three methods through these two scenarios. And the results, well, they were pretty dramatic.
The results couldn't have been clearer. First up, the Fubini study method. Could it tell the difference? Nope. It gave the same complexity value for both paths. That's a fail. What about the covariance matrix method? Same problem. It was completely blind to the state's history. Failed. But then there was circuit complexity, and it absolutely nailed it. It passed the test with flying colors. And you can see exactly what it found right here. It correctly calculated a lower complexity for the simple one-step process, and, just as you'd expect, it assigned a significantly higher complexity value to that more complicated two-step round trip. It could actually see the extra work involved. So what's the big takeaway here? Circuit complexity won because it's the only one that gets a really simple, intuitive idea. The journey matters. A state that has a more tangled, complex history is fundamentally harder to build, and this was the only ruler that was sharp enough to detect that. Okay, so this is all very cool. We have a winner, a better ruler for this weird abstract thing, but why should you care? Well, It turns out this has huge implications, stretching all the way from the inside of a black hole to the future of computing.
Let me break it down. First, and most obviously, we now have a ruler we can actually trust, a reliable way to measure quantum complexity. Second, this is a massive clue for understanding gravity. It gives us a real tool to test that wild idea that the inside of a black hole is literally a physical representation of growing quantum complexity. And third, this is super practical for quantum computers. If you can accurately measure complexity, you can figure out the most efficient, least complex way to run a calculation, which is absolutely critical for designing better quantum algorithms.
In fact, the researchers took their findings and proposed a new general principle. Basically, the more steps and detours in a state's history, the higher its complexity will be. It's this simple, elegant rule that was just hiding in plain sight, waiting for the right experiment to uncover it.
And that just leaves you wondering, doesn't it? If the secret to what's inside a black hole was hidden because we were just using the wrong ruler, what else is out there? What other profound secrets of the universe are just sitting there, waiting for us to invent the right tool to finally measure them?